Example 3 for area between curves. As we begin this problem, I look at my two functions, my two curves. As I see these curves, I notice that they're solved for y, which means everything's in terms of x. It almost guarantees that I will have a vertical slicing. So I take a look at my graph here. I'm going to do a crude graph as I've done before. For the first function, it looks a little something like this. It's a cubic, so it comes up like this, goes down, shoots right back up. And for the second function, it's simply a linear curve. And so I draw that. This is just a crude rendering, it doesn't have to be perfect. And what I'm interested in is the area caught between these two curves. As you're looking at this picture, you actually have two regions. You have this region right here, and you have this region right here. As I talk about these two regions, I obviously need to know where these curves are intersecting, but then I also have to recognize that my top function for this first region is the black, and then I've got this linear function on the bottom. And when I go to the second region, those things are reversed. It is the red function, or the linear function, and then the black function there. So I have to break this up into two different integrals. And that's what I'll do down here. I'll say my area equals the integral. Now I have to figure out what these points of intersection are. And so I'm going to do that right now before I write all this. Leave myself plenty of room. I already have this graphed on my calculator, and so I'll go second calc, I'll find the points of intersection, first curve, second curve, and do a guess right there, and that gives me a value. So I'm going to start with the leftmost value, which is negative 1.5645. I'll find the next value. All I did was put the lower boundary here, the lower limit. Second calc, option 5. First curve, second curve, and get close to that point there. And it tells me this intersects at 1.4253. 1.4253. And I might as well find that third one. So I go second calc, point of intersection, first curve, second curve, get close to it, boom. And now that tells me, I'll show you what I'm writing here in 1 second. 1.4253. The second point of intersection was 3.1391. 3.1391. What I've done, this is the first region. That first region would be right here where my finger is. It starts at the negative 1.56. It ends at 1.42. Well, where that first region ends, the second one begins. So I begin the second integral at 1.4253, and I end it at the third point of intersection. So in other words, this point right here was linking the two regions. That's where it was switching from the black function being the top to the red function being the top. So I picked up right at that point. Now here, obviously, I'm going to have to write those out. And so I'll start off with that curve, because I'm talking about this region right here. So I start off with the curve. I do my x cubed minus 3x squared minus 2x plus 3 minus the 2/3 x minus 4 dx. Again, it's very important that you notice that I'm always using my parentheses, because I need to distribute this negative across there And that's going to cause some issue if you do those backwards. For this one, this is going to be the second region. All I'm going to do is switch the order of this. So I'll say this is 2/3 x minus 4 minus x cubed minus 3x squared minus 2x plus 3 dx. And then I'm going to have to go to a new piece of paper here to simplify all this. Technically I wouldn't have to simplify it. I could just type it all in the calculator if I didn't want to go through this process. In fact, I think I'm going to do that just to show you that your calculator can handle this. Your calculator doesn't care what you type into it. It's a computer. It doesn't have feelings. So if I do that first region right there, I simply say x raised to the third minus 3x squared minus 2x plus 3 minus, now I need to put parentheses on there. See, that first part, none of the signs were changing, but this would change. So if I'm not going to change them as I type them in, I need to put parentheses there or change each one of those. Call this minus 2/3 x plus 4 or type it the way you see it. So I'm going to type it the way I see it. And then I can hit graph. Now for that first region, I can simply go second calc, go to option 7 there, and it tells me where to start. I want to start that first region at negative 1.5645, and I wanted it to end at 1.4253. Now that gives me an area 14.2926. So that first region was 14. Let me do this in a different color. I'll do it in red. This was giving me 14.2926. And then in the last video you saw that I screwed up on these values right here. I had them reversed and it ended up giving me a negative answer. I'm going to build off of that because when I look at this, isn't this just going to be that negative region? It's going to be the same function. In other words, if you type these in reverse, it simply reflects this curve over the x-axis, and you'd have this little nub that comes up here and this would be all down there. So instead of me retyping it all, I can just take this area and whatever it gives me turn it into a positive, or if I wanted to I could switch these boundaries on that. Actually in the calculator it may give me an error for switching that, but the concept would still be the same. Let's try that and see what happens. I'm going to go second calc, do option 7 there. I'm going to reverse those and see what it does if I do it in reverse. So I'm going to start with this 3.1391. and then I'm going to go 1.4253. No, it did do it. Okay, so it understood that I was going to go in reverse, and because that's beneath the x-axis, technically it should have been negative, but because I went in the reverse order, it does report a positive value. And so I can just type that right in there and say plus 3.2271. 2271. And of course the last step would simply be to add those two values. So I'll go home on my calculator. 14.2926 plus 3.2271. I get 17.5197. Now we like to round our answers 3 decimal places, so I'm going to try and squeeze that in here, and we'll go 17.520. As I put that as 520, it's not 52, it's that 0 is significant. It's telling me that I rounded to that, so it's 17.520. There is a third example for area between curves. Area between curves. On this one I was given those boundaries, I had to find those. As I found those boundaries I made sure that I linked it. So this was my leftmost, my middle point of intersection. Then I had to start at that point of intersection and go to that third point of intersection. So that gave me one region, two region. And there's all my work for how I came up with this area. And that is the total area between these two curves. So now I can mess my drawing all up. That's what I was finding, was that area between those two curves, and it turned out to be 17.520. And for a third time, this third example, recall that when you look at these areas, they won't always, and most times they won't, look exactly like your curves. If you draw those out, that curve is going to look different than when you're using your calculator to do those areas, because it's pushing that area up and it's basing everything off of that x-axis. So that's not anything to freak out over as long as you are setting up your integrals properly. This is our third example for area between curves.